Hello there, I am Renato, the instructor for the online materials of Advanced Digital Signal Processing. This is a course offered by Professor Schule at the University of Technology, and on this tutorial we will talk about Wiener filters. So Wiener filters are filters to reduce the influence of noise or distortions, and on this notebook the highlight will be when we will have a Python example using Maiden, the number of the beast intro. This is very classic speech, and we're going to implement a Wiener filter using a sci-fi signal, and there's all this example. So let's get started. Wiener filters are filters to reduce the influence of noise and distortion. So let's assume we have x of n, that is the original signal, and we have y of n, which is our distorted signal. So here we have that y of n is equal to x of n plus v of n, where v of n is assumed to be independent white noise. So Wiener filter will have this hw of n, will convolve hw of n with our distorted signal, and we'll get back our x of n, our original signal. So that's the idea what we want to achieve. So signal fidelity, so the reconstruction is close to the original. For instance, for denoising an image or audio signal, where the audio signal does not need to be deterministic. The goal here is an approximation of the original signal in the least mean square sense. So meaning we would like to minimize the mean quadratic error between the filtered and the original signal. So if we have a filter system with Wiener filter h of w, we have here x of n is equal to y of n convolved with h of w. So this is our Wiener filter, this is our distorted signal, and this is what we want to get back as our original signal, or an approximation of the original signal, meaning that we filter our distorted signal y with our still unknown filter hw of n. So the convolution of hw of n, so this is filter length L with y of n, can be written as a matrix multiplication. So alternatively, we can run the sum in the other direction. So this is property of convolutions. So now let's define two vectors. The first vector of the past L samples of our noisy signal y up to the present sample at time n. So both phases here are indicating that it's a vector. So this we're defining here our vector. So past L samples of our noisy signal up to y of n. So the next vector contains the time reversed impulse response h of w. So this is using those two vectors, we can rewrite our convolution equation, this one or this one, as a vector multiplication. So this x of n is equal to y of n, this vector we constructed here, multiplied by this vector. This is the time reversed impulse response here. So observe that h of w has no time index because it already contains all the samples of the time reversed impulse response, and it's constant. So we can now also put the output x of n into a row vector. So we are transforming our signals into vectors. To obtain this column vector, we simply assemble all the row vectors of our noisy signal y of n into a matrix. So we have this matrix with our y of n, and with this matrix we obtain the result of our convolution at all time steps. So this matrix times h of w is equal to x of w. So we're implementing a convolution, but as matrices and vectors multiplication. So this is just another way of writing our convolution. So for example, if we have a filter of length 2, and this is h of w, so we have here our matrices of the distorted signal. We will multiply with this filter h of w, and we will get our x. Observe again that the vector h of w in this equation is the time reversed impulse response of our filter. This is now the matrix multiplication formulation of our convolution. We can now obtain the minimum mean squared error solution of this matrix multiplication using the so-called Moore-Penrose pseudo-inverse. So here in Wikipedia you can read about the Moore-Penrose inverse so you can understand what's going on. As this pseudo-inverse finds the column vector h of t transposed, which minimizes the distance to a given x with the matrix A, which contains our signal to be filtered. So A times h of w transposed will imply to x of t transpose. So matrix A and vector x are known. This is done in a training phase to obtain the Wiener filter coefficients from noisy signals in matrix A and clean signals in vector x. And vector h of w is unknown at the moment. After the training phase, the filter can also be applied to similar signals. So this problem can be solved exactly if the matrix A is square and invertible. Just multiplying the equation with A to the power of -1 from the left would give us the solution. So now we have here the h of w is equal to A inverse times x of t. This cannot be done if A is non-square. For instance, if it has more rows than columns. In this case, we don't have an exact solution, but many solutions that come close to x. We would like to obtain the solution which comes closest to x in a mean squared error distance sense. So this is also called the Euclidean distance. So this solution is derived using the pseudo-inverse. So we have A transpose times A times h of w transposed equals to A transposed of times x transpose. So here A transpose times A is now a square matrix and usually invertible, such that we obtain our solution h w transpose is equal to A transpose times A to the power of -1 times A transpose times x transpose. So this h of w is now the solution we were looking for, and this solution has the minimum square distance to the unnoisy version of all solutions. It's always good to try out and to understand better this a bit complicated theoretical mathematical formulations using a Python example. So here we're having a Python example for denoising speech. So the first part here, we're importing our Python libraries. We are going to use a SciPy signal and NumPy to handle calculations. We are going to use IPython display to listen to some sounds. We are going to use import to librosa and wave to load audio files, and we're going to use struct. So this is in conjunction with import a wave that is going to use here in this wave read functions we are defining. So librosa has this very convenient way of loading audio, but also is interesting to see this different approach using this wave library. So here we're defining this wave read. It takes as an argument sound file, so we call wave open sound file. So then we have this part here. We're getting the number of channels, getting the samples, the sampling rate, number of bytes per sample, and here we're plotting here. So it's a mono, one audio, 2 bytes per sample, 16 bits. Sampling rate is 32 kilohertz, and this is the length of our audio. So this is how now we're using this struct to unpack and transform it to shorts. And here we have our, so let's run the cells, and here we can listen to our audio.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So this is the speech we're going to work first. Later on we are using Maiden, which is much more exciting than this example here. But now we are going to add some noise with zero mean white noise. So this is what we are doing in this part here. We're using the NumPy random to add noise. and this is the noisy signal.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So we see there's a lot of white noise there. At this part here, we are transforming our arrays X and Y into matrices and transposing them into a column. And here we are defining this A matrix. So we are going to use 10 coefficients for our Wiener filter. And this is what we're doing here. We are building this matrix A. So here we have our noisy signals Y. And we can see that there is a shape of 100,000 rows and 10 columns. So this is our matrix. And here we are computing the Wiener filter. So the trick here is to allow a filter delay, the flipped filter delay of 5 samples to get a better working denoising. Yeah? This corresponds to the center of our Wiener filter. So then the desired signal is going from 5 to 100,005. So we're having this delay of 5 samples to get better denoising. And now our X and Y are matrices, and when we use this operator star, this is the matrix multiplication. So our H, now we're having here this A transpose times A transpose times X, and then like we've seen in these equations here we have this here. So here's the impulse response of our Wiener filter. Observe that this is the non-flipped impulse response, and we see we have a delay of 4 samples. So the peak is at sample number 4. We can also see here the frequency response using our old friend FRAC-Z from SciPy signal. And here we have our frequency response. Here we can see that the resulting filter has a somewhat low pass characteristic because our speech signal has energy mostly at low frequencies. At high frequencies we have mostly noise, and so it makes sense to have more attenuation there. This attenuation curve of this Wiener filter also has some similarity to the speech spectrum. If we compare it with the spectrum of a white noise, then we see that at low frequencies the speech is dominating, and at high frequencies noise is dominating. Hence we need to remove or attenuate that later, this noisy part of the spectrum. So here we can plot the spectra of speech and noise together. This is what we are doing. We have speech, noise. Here we have in red is the white noise spectrum. Here we have our speech spectrum in blue, and also we are plotting the Wiener filter. We're just giving it some shift to get closer, and we can see it has some shape that kind of goes along with speech. Here we see that speech dominates the spectrum only at the low and middle frequencies. Noise dominates at other frequencies, and it makes sense to suppress the noise frequencies. So now we can use L filter to filter. So we need to convert the matrix back to a one-dimensional array, and this, so we are using filter here. We are flipping the impulse response. We are transforming it into an array. Also transform our Y back into an array. In this we're applying the L filter from SciPy signal, and what we have is
to administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So let's go back to the original.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Okay, this is the noisy.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
And now the filtered version.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So we can hear that the signal now sounds more muffled, The high frequencies are indeed attenuated, which reduces the influence of the noise, but it is still a question if it actually sounds better to human ears. We can see there's still a lot of noise there. This Wiener filter could now also be applied to other speech signals with similar frequency characteristics for signal and noise. Yeah? But now let's compare the mean square quadratic error, the MSE. So this was the optimization. What we wanted to do here is to have this mean squared quadratic error to see if it's reduced using this filter. So this is for the noisy signal. We are computing here the mean squared quadratic error, and we have this value here. So here we have for the Wiener filter signal. We need to take into account this 4 samples delay from our filter. So we have this shift here to compensate this 4 seconds delay. But we see that there is indeed much less. So maybe it's almost 2 times less than the noisy version. And we can also take a look at our matrix A transpose times A, which we used in the computation. So it has now a shape 10 by 10. So we have here it's a 10 by 10 matrix which shows a Wiener filter with 10 filter taps. And in this matrix, the next row looks almost like the previous line, but shifted by 1 sample to the right. Observe that in general, this matrix A transpose times A converges to the autocorrelation matrix of the signal Y of n if the length of the signal in the matrix goes to infinity. Here we have the autocorrelation of signal. So this is RYY. Here was A transpose times A. And converge to the autocorrelation matrix here. Since one row of this matrix is the shifted by 1 sample version of the above, this is called the Toeplitz matrix. So the expression AT times X of t in our formulation of the Wiener filter now becomes the cross correlation vector. So we have A transpose times X transpose. So this is the cross correlation function X of Y. So we can see that in the receiver, we usually don't have the unnoisy signal X, but we can estimate the above cross correlation function. So our expression for the Wiener filter H of t transposed all this, and it becomes this RYY inverse times small r xy. So this matrix form is also called the Wiener-Walker equation, and the general statistical formulation is called the Wiener-Hopf equation. So you can see from this book, Statistical Signal Processing and Modeling, you can learn more about this Wiener-Walker equation and the Wiener-Hopf equation. So this general statistical formulation now also has the advantage that we can design a Wiener filter by just knowing the statistics, the autocorrelation function of our noisy signal, and the cross-correlation function of our noisy and original signal. So observe that this autocorrelation and cross-correlation can also be obtained from the power spectra. So the cross-power spectra, the product of 2 spectra of the respective signals. So the power spectrum of the noisy signal can usually be measured, since it's the signal to filter, and the spectrum of the original signal Xn usually has to be estimated. So we need to using assumptions about it. So for instance, we know the typical speech spectra. If we want to adapt a Wiener filter in a receiver, we take this typical speech spectrum and we measure the noise level at the receiver. Then we can add the power spectrum of the noise to the power spectrum of the speech to obtain the power spectrum of the noisy speech, which is the power cross spectrum of the clean speech and noise, or the Fourier transform of cross correlation, because we assume that speech and the noise to be uncorrelated. So to use this Wiener-Hopf, we simply apply the inverse Fourier transform to the power spectrum, and that is sufficient to compute the Wiener filter coefficients using the above formulations. So to close this notebook, we have one more example, but now we are using the SciPy implementation of the Wiener filter. So SciPy has this signal Wiener that perform a Wiener filter on an n-dimensional array, and we are going to use the classic Iron Maiden, the number of the beast introduction. And here we see there's a different approach. So this implementation of the Wiener filter, if we don't give the noise power as an argument, the noise is estimated as the average of the local variance of the input, and this is what we are going to use. So we have here, let's listen to the original signal. So this is Iron Maiden, the number of the beast. So this is the original. Now we are going to add some random noise like we did before, and then so we see, we listen that there's a lot of noise there. Now we're going to use the SciPy Wiener filter. So we are not passing any noise power. We are going to use the noise estimated as the average of the local variance, and we are going to give it higher order. So we are going to go the filter size of 51 taps. So the size here should be odd, and we are using 51, and let's see what's happening.
Let him who hath understanding reckon the number of the beast. For it is
we listen that it removes a lot of the noise, but also it gives the speech, removes a lot of the part of the speech. So we can try, for example, to use less coefficients and see what happens. So,
let him who hath understanding reckon the number of the beast. For it is few. Its number is 666.
so yeah, we have here, there is some noise reduction, but it also affects the quality of the reconstructed signal. Yeah, but if we compare to,
let him who hath understanding reckon the number of the beast. For it is, let him who hath understanding reckon
it becomes more intelligible. We can understand better what's going on, and it was the SciPy. Now, if we also check the mean squared error, and we see that there is a very, very high reduction in the filter. So the Wiener filter is doing what it's supposed to be doing, and it's a matter of fine-tune it, choose number of taps to have a good estimation of the noise power. And that's it for today. See you next time.